So good morning, good afternoon, good evening, everyone. So from part of the globe you're listening. Welcome to the tutorial with the title Formal Automated Code Checks to Accelerate Top-Level Design Verification. And for the next hour, I will be talking about the top-level design verification from the automated code checks with formal. My name is Nikolai Tushinsky. I'm a senior field application engineer at OneSpin, and I will guide you through the current today presentation. So before I start, can you confirm if you hear me well? And we can move on.
Yes, we can hear you.
Okay, all good.
Şeyi alabilir mi yemeğini? Ödev
Sorry?
yaptın mı? Ben şimdi seni...
Okay. So before I go into the today presentation, I wanted to discuss to bring out how important it is to detect the early bugs in the process, in the verification process, design process. And this picture still amuses me because it's very relevant to the field of application we are working on, and mainly the bugs that we are hunting for. The later we catch them, the nasty they become, and therefore the effort to get to fix the bugs that are later detected in the verification process are becoming more costly. And exactly this is a graph that displays also some graph on how the specific phases into the process, and we see that if the bug is detected during the design, it comes at mostly no cost compared to fixing a bug that is detected in the implementation and not and it's getting worse if it goes into the production. So what I will be covering today is the current formal adoption in the industry and why the formal adoption is increasing year by year. Then I will jump into formal, demystifying how formal and simulations work together, how they differentiate, and specifically what are the differences and the benefits. And then I will introduce the OneSpin DV Inspect, which is the solutions that represent the automated code checks. So no user written assertions are part of. So the automated checks that are info from the RTL. And then the topic that I believe is the most interesting: how do we scale up from the block level to the top level design using automated code checks? So yeah, formal adoption. We've seen that formal and simulation are working together pretty well and the number of flows that this approach is getting is increasing. So but before we make these two technologies methodologies working together, we would need to figure out what fits best. For that reason, it is important to use the right tool for the right problem, because this saves time and money and avoids frustration in the end. So it's very important to use the right tool for the right job. For example, in a highly parameterizable IP, it's not so good to target with simulation. On the other hand, having formal used for an analog design is a dead end. So we see an increasing strong formal adoption in the industry. So this is the part is increasing. So formal is increasing in the verification process, and And for that reason is there are a couple of reasons why this is happening. So the inadequate verification. So basically, this is some research data coming from the year 2016. It's not so far from the reality. So in the industry, we have 74% respins caused by design errors. Then, as we know, the verification consumes a large number of product schedule. And the most significant here is that with all the computation power that is increasing, we have a stronger and more powerful formal solution. So therefore, the formal becomes an alternative to several verification targets that previously were targeted with simulation. And this strong adoption is also due to that formal is getting more and more automated in the past years. So yeah, as we see that the number of projects that are using formal is increasing compared, and it also is not only the formal property checking. This is the user written assertions that, but also the automated formal applications. These are getting the usage of automated formal checks is getting increased over projects, and yeah, this is a good trend that formal is working together with simulation, and it's important to get the verification process more efficient. But how formal works, and I'll try to demystify this for you, is first let's bring the simulation. So basically in simulation, one would need to apply an input stimulus, apply a clock, and the design will move to design, and this will move the design to next states that will do the exploration. On the path, this may reveal bugs. If the state is hit that contains this erroneous behavior, so there may be several bugs until the coverage item is hit. One would then try to use UVM random simulation seeds to uncover new state spaces and discover more bugs. But even after extensive simulation, there is a significant state space that remains uncovered. And this state space that is left uncovered, in most cases, there are bugs that are hiding in those specific spots. How formal works compared to this the simulation is that formal will start with the desired state and will work backwards to create exhaustive proof, and this will verify an extensive state space in the process. There may be bugs in this state space that is being explored uncovered. Then another so-called checker will explore more states and uncover more bugs. Therefore, the state space that is covered by formal is increased compared to simulation. Therefore, there is a drawback because this is, as you can see, is an extensive state space exploration, and this is what we're going to talk in the second part about. So formal is also good in detecting specific targets that are hard to reach with simulation, and this is these states that are uncoverable. So this is the dead code that is easily detected with formal, and is not so trivial to identify it with simulation approaches. So yeah, summing it up, so formal is exhaustively applies checks to all states and transitions, requires no stimulus, which is the biggest advantage to simulation. It is concise and complete. On the other hand, simulation checks one sequence of states driven by stimulus to replicate the operation. It relies on user test vectors, and also it's tedious and error prone. So with formal, there is high coverage higher coverage, and this coverage is achieved much faster. This will bring me to the one-spin DV inspect. So one-spin DV inspect is the solution that will help to accelerate the design verification flow. It enables the so-called designer-friendly shift left. And how it does, it easier removes bugs early than to discover them during verification. So simulation and linting tools can be unnecessarily time-consuming. On the other hand, the formal technology provides precise, high-quality results. There are several types of checks that will enable an efficient block verification for a cleaner chip level integration, and this will increase the designer satisfaction and reduce the time spent for verification. And the most important, there is no need to set up any stimulus, and because this is an automated flow, and the only input to the one-spin DV inspect is actually the RTL itself. So formal is the key enabler for shift left, and this is a graph that reflects why simulation is the time consuming, especially the first part, where you can see that there is a decent amount of time spent on setup. Well, on the other hand, having formal will reduce this setup time. Therefore, the bugs are being identified much faster, and the project time is being reduced faster with getting faster simulation and faster coverage closure in the end. So yeah, the number of bugs also gets increased. The number of bugs identified in the process is increased in the early stages. So one-spin DV inspect is part of the one-spin 360 design verification solutions. The verification solutions are sharing a unified platform, so there is a unified platform for this, and the DInspect is the entry level, I would say, that comprises several type of checks. So DVinspect performs a structural analysis. There are activation checks and safety checks, and also it provides a coverage closure acceleration, so with an app that helps to close coverage faster. On top of that, once on the DVinspect, there is the DVverify solutions. So these are apps that are automated, and also the user written assertions are part of the DVverify solutions together with the coverage solution. So these are apps, verification IPs, user written assertions, and the coverage solutions are part of the DVverify solutions, and they are coming on top of DVinspect. But today's topic is DVinspect, and let's see how how DVinspect is actually helping, and what type of checks are in the solution. So yeah, as you've seen from the previous slide, DVinspect are mainly classified in three types of checks: the structure analysis, this is the one-spin lint part. Then we have the activation checks, this is the reachability part, and we have the safety checks. The safety checks are actually assertions that are synthesized from RTL, and these are very important because if you have a failing assertion from the safety check category, then most likely there is an issue in your RTL. So yeah, it helps to catch a broad range of issues, if you can see here. So for the safety checks, these are actually classified in more categories, like runtime errors, simulation synthesis issues, and safe functions. So and there is a list of checks. Here are only a couple of examples that what type of checks are available in DVinspect. So in OneSpin tool, these type of checks are actually grouped. So the safety checks, which I was talking, are grouped into a tab under model building. Mainly there is a list of checks that are ending up in the model building. These can be checks that, if they are failing, can trigger a simulation runtime error or simulation synthesis mismatch issue. They are actually part here in the model building tab. On top of that, we have several other categories. So we have the initialization checks, which are also part of the DVInspect. We have the general checks, and then we have the reachability part, which is the FSM checks, the stick checks, which are covering the toggle checks, and the never from value to value checks as well. And the deadcode checks are part of a separate tab that you can see here. So this is how the grouping is actually done in OneSpin tool. And we will go into exploring each category individually. So in OneSpin DVInspect, the first we're going to talk about is reachability analysis. And when it comes to reachability analysis, FSM checks is an important part of the every design verification, and it is important that for each FSM that designer has designed encoded in the RTL, it's important that these checks are actually the states and the transitions are actually reachable. So OneSpin detects automatically the state machines in the RTL, and for each, and it creates a matrix on how this FSM is being encoded. So the FSM checks are have a set of subchecks that cover the state reachability and state transitions. So the state reachability verifies that each state in the FSM is reachable from reset. And the state transition verifies that all transitions between states that are coded in the RTL can be taken. And on top of that, there is the deadlock checks that verifies that if a state can be reached, there is always at least one way to leave this state, not including reset. So the detected FSMs can be automatically drawn in a bubble diagram form, as you will see shortly. And yeah, so this is the metrics view that is displayed in a OneSpin tool for an FSM. What does this metrics view represent? So you have the states on one side, and then you have the transition. So for example, for state blocking here, we see that this state is covered in one cycle from reset. So basically there is a way to get into this state one cycle after from reset. Then we have the transition, which is actually encoded in this metrics view here. So we see that the locking to idle transition is covered in 3 cycles from reset. Of course, we have dead states that cannot be covered. In this case, the state dead here cannot be covered, and therefore the transition from dead to idle cannot be covered as well. And the empty spaces here with the dash dash, this is actually transitions that are not encoded in RTL. So from RTL, this matrix is extracted, and the tool is detecting that, okay, for the dead to locking or dead to over constraint, there is no such transition encoded in RTL. So from inspect, you can see that, okay, you have the metrics view. Then for each FSM, you have a general check that is accompanied, comes together with this metrics view. And if there is desire to visualize the FSM into a this one here. into a bubble diagram, then which is more familiar to designers. In fact, this is also possible with a simple command call, and such a nice bubble diagram will be shown, which will actually reflect the state of the FSM check. So for example, you can see, okay, the error is dead here, so we don't have any, it's a deadlock here. And the transition from enable to enable, you can see that the looping transition exists but cannot be exercised. As I pointed out, yeah, for the error, once entered, this can only exit via the reset. So this is the a graph that describes in more details what type of checks are possible, can be extracted from RTL by one-spin DV inspect. You have the general checks and the model building checks. The model building checks are the one that may trigger a simulation runtime error or simulation synthesis mismatch if this assertion fails. So these type of checks can be a array boundary violation, division by zero, function without return, range checks, signal domain checks, parallel case violation, full case violation. And then we have write races, process overwrite, and some other checks which are not listed here is also a part of this model building checks. General checks, this comes, excuse me, general checks comes from, we have the activation, which I already talked about, the FSM checks. We will cover the dead code and stick checks in a moment. And then the safety checks are also part here. But what I want actually to talk about here, because we have an extension to the FSM checks, so that translate not to perform the activation and the reachability analysis, but go beyond that, and namely the deadlock livelock app, which is a functionality included within inspect. And what actually this app is doing, it checks for deadlock and livelock and performs a stronger analysis to identify these conditions. As you can see here, for this specific FSM, you have a check, which is an assertion check that fails in some thousands, some 10, 22K number of cycles from reset. And this is the result of the deadlock livelock app. And this failure, it actually can be debugged. So you can see that, okay, you might have the debugging infrastructure for such checks. As you can see that these livelocks are deadlocks and livelocks are including liveness properties. Therefore, you're having the long number of cycles. But it's important that this is stronger analysis is possible to identify livelocks, and this utilizes the some advanced formal engine capabilities to identify this deep livelock deadlock behavior. So it's significantly more advanced than inspect FSM analysis. And if someone is interested in having a thorough check on the FSMs, then using the deadlock and livelock app is encouraged. All right, so now that we complete the FSM checks, the next in line is the dead code checks. So these are the checks that identify that if a code statement can be actually exercised. So it's these are cover properties synthesized and formally checked for each code region. If you get a fail, this means it's unreachable, so it's proven to be dead code. So, and it also shows that is not reachable within n steps from reset. So in case this is reachable, it shows, you can see with a witness. So it's a trace that comes up with the results showing that how this code is exercised. And you can leverage the unique activation, unique code activation annotation and signal tracing capabilities to actually identify how this is being triggered. So with that code check results, you get a hold and a fail. A fail means this is unreachable, and the hold, you can see that this piece of code can be exercised from reset, and you can see actually how this is happening. In case of unreachability, then the question would be like, okay, can we debug it? Yeah, you need to manually inspect the code in order to identify the reason for that code happening. So usually the reason is located in the condition of the statement that is guarded by that condition. So usually it's the condition that is the reason why this is not cannot be exercised. On top of that, we have the stick checks. So these are checks whether signals checks that whether signals are constant or can toggle. So of course, after reset sequence is applied. So the state signals, the stick checks are actually covering the enum type and non-enum type. And in case of the enumeration type, then there are 3 checks generated per signal. And in case of non-enumerated type, there are 4 checks. And you can see here that for enumeration type, you have a check that is constantly value, never gets to value, and stuck at value. And for non-enumerated type, we have a checks for constant 0, 1, and then the toggle from 0 to 1, 1 to 0. So such a check fails if at least one of these checks is failing, and therefore the results are also visible. So you get the same results as in the case of the code, you get a hold and a fail. So these are the stick checks. So the checks that these are, in a nutshell, are the reachability checks, the checks that make sure that the code can be exercised on signals, FSMs, and the statements separately. And this brings me to the next section, which talks about the safe RTL checks. So these are the assertions synthesized from RTL. And these type of checks are classified under the model building category. So these checks are identifying RTL issues that may corrupt the verification model. So there are 2 subcategories, as I already said: simulation runtime error, simulation synthesis mismatches. These checks are required to hold in order to validate the model building, and the violation of a model building assertion would raise a runtime error in a simulation environment, or a deviation between the simulated and synthesized behavior. An example of such a safe RTL check is an array access out of bounds. Here is a piece of code that reflects exactly the problem. So that this 3-bit index used to access array with 6 elements. Therefore, this using a static linting will point out it as a potential out of bounds access based on types. But the key word here is potential, where on the other hand, if you have an assertion on this type of checks, then a failure will show exactly how this out of bounds is happening and how the violation is actually happening. So it either proves that this access is never out of bounds, or shows a simulation trace from reset with a boundary violation. Well, the next in line are actually the optimization checks. These checks are grouped under the general category, general tab here. And these checks are optimization because they might reveal an issue, or they actually might be that this is just a nice to have. For example, in this category, we have the truncation checks, which are actually talking about the overflow and underflow. We have other categories like integer and shift, but when it comes to truncation, it's important to understand that in some cases, let's take an example, a counter, that a counter can wrap around, and then this will be detected as a violation, but in fact, this is actually expected. On the other hand, if you have a truncation violation in some arithmetic module, then this might lead to some wrong results. So therefore, are classified as optimization checks. So the integer checks are actually identified with redundant bits, and shift are actually checking that in case of shifting, the negative shift or the positive shift is filled up with the corresponding values. Of course, linting is not omitted from the DV inspect. So this is part of the DV inspect, and the autolint from OneSpin is that there are issues that are collected during the read phase, the elaboration phase, and the compilation phase, and depending on which phase has been performed, the number of lint issues that are identified in RTL are piling up into a text that can the user of the tool can see where in the source this lint issue is actually located and what type of issue it is. So there are around 300 plus issues that can be highlighted. So this is at least a number that me personally have listed. Maybe there are more. So yeah, so these issues are actually piling up during the read and elaborate and compile phase. All right, now that we know what are the capabilities of a OneSpin DV inspect, what type of checks we have, and what each check is actually covering, then let's talk about how we address this for top-level designs. So there are different verification approaches, and the most common are the top-down verification approach, specification-driven one from system to individual components. And then there is the opposite one, the bottom-up verification approach from individual components to the system. So when it comes to automated checks, I would say that the top-down verification approach is not recommended, and I will mention why. Because the bottom-up makes more sense, because you would like to get your block levels clean from the beginning, and when you move up to the integration part, these the local bugs that are not going to reflect a bigger issue that is harder to debug when you move up into the hierarchy. So yeah, the bottom-up verification approach has advantages. So it's the locality, it's easier to catch bugs, and it's faster actually at block level. So there's not so much noise during the debugging process. And during the design of the SoC chip with this, I mean, identifying issues at the block level, when you're designing the entire SoC chip, these bugs will not propagate up. And then it's important to have these bug-free blocks when you're doing the integration. So yeah, for bottom-up verification approach, what we recommend is to make the block level green. So in this diagram, we have a system that has a cache, a CPU, some protocols that help to integrate. And it's important to get the blocks green with the automated checks. And this is actually a prerequisite, I would say, step before you're performing any integration. So before you're doing integration and before you're trying to verify that everything is integrated correctly with the verification IPs, with the register maps and the connectivity apps, it is important to have these blocks green. But there is always a problem because the complexity is continuously increasing, and we've seen that the industries are actually getting more complex designs in different type of applications there is a massive acceleration. Therefore, everything is still integrated on a system on chip. And what you previously had to hold at the block level, when you verify with automated checks on from the top level, when you integrated everything and you want to rerun your auto checks, usually these checks do not converge as fast as they did on the block level. And of course, this is expected because you have the state space to explore is increasing and so on. But this is not a dead end, because usually there is ways to get to convert on checks that are actually of interest. So what the first step would be is to make sure you're having the right setup. So your setup from the block level, when you're moving to the top level, might not be the same, and therefore it's very important that when you're trying to verify an auto check with DV inspect on the top level, you need to review that the clock specification is properly specified. Although the clocks and the reset sequences are extracted from RTL, it is still important to verify that there is a correct one. Then there is in one-spin DV inspect, each check is can be the time or the computation power to be spent on several categories on the check run can be specified by the engineer with effort levels, and this is predefined effort levels that help to get more checks to converge. And usually these effort levels are proof strategies that differ from medium, high, super, maximum, and there is always a trade-off between runtime and precision when we are dealing with this effort level. So by default, we would like to get as many checks to converge as possible. But when we go up to the top level, this is usually when, imagine you're having 100K checks only for stick checks, and then you have another 10K of some other checks. This is usually would need some thinking on what you would need to verify first. Then when the effort level is still you're having checks, another way to deal with the top level automated checks is try to reduce complexity. How we do it is important is to identify the source of unnecessary complexity. Usually when you're having an SoC or bigger design, you don't, you most likely, if not 100%, you'll have counters, large memories, multipliers, adders, and some other blocks that actually are not so formal friendly in the end, and therefore it is a good hint to identify this and to isolate them. You can identify this with some functionality in one-spin design statistics. You can get them reported, and then this will list all the important information in the design, like counters, memories, adders, multipliers. These are actually listed here. So yeah, the first step into reducing this complexity is to get this element from the design. When we reduce the complexity, now we'll focus a bit on the counters, because this is one of the sources of non-convergence when it comes to the top level designs. The idea is to have these counters cut. So this is a common way to deal with complexity. So basically cutting the counters. Therefore, the counters will become a new primary input, and this is now will be treated as a primary input, and therefore the tool will lead this primary input and will get over the counter complexity, but this is a disclaimer that in some cases this is not 100% to help, because some of the functionality may be damaged from this. So therefore, this complexity reduction needs to be treated accordingly and needs to be reviewed. Another way to reduce the counter complexity is to actually do not cut the counter, but to deal with the counter values and to identify them, to classify counter values as that are driving as interesting, and to abstract these intermediate values. And therefore, this is a more accurate way to deal with counter complexity, but in some cases, this is not so true. So this would need to identify counter values that are actually interesting. So this is another way of dealing with complexity. Another way to deal with complexity, there is a common concept in formal, is the black boxing, and the idea is to cut out certain parts of the design. And this is usually a way of doing it when you are dealing with large memories. So basically, memories are not always a point of interest for formal verification. Therefore, in order to reduce the complexity, these memories are being abstracted by the black boxing. What happens when you do the black boxing? You are getting that the output port of the black box of the module B becomes primary input, and the input port of module B becomes primary output. This gives more freedom to the formal tool. Therefore, in some cases, you might end up with unrealistic behavior. But if you isolate this behavior by putting some constraints on this new input, then everything should be all right. So yeah, as I pointed out, it's usually a way in formal verification to deal with missing or non-synthesized or too complex modules. And the last one that I would like to talk about is actually when we are dealing with very large designs, and it's important to figure out what exactly needs to be verified first and what to focus on, and allocate more resources in the end. So how we're dealing with hard problems is to build strategies for better results. Therefore, you have here like 3 buckets, I would say 3 clusters that needs to be verified. They deal from easy problems, medium problems, and hard problems. And then we have the inspect, verifying cluster by cluster. So for easy and medium, there is no blocking point. But then when it reaches a cluster that has a very hard problem, it cannot go on to the next problem because it needs to finish the hard one. Therefore, the time is up, and there are easy checks that could have been identified quicker. And here is where the strategies are coming into place. Therefore, and that's why it is important for the clusters to allocate decent amount of time such that the easy and the medium are identified faster. And if hard problems are hit, then we are working on them, and then we are returning to finish them up later on. And how does this actually reflect on the process? You have the easy and the medium problems being verified from the first cluster. The first cluster is done. You're moving to the next one. You hit a hard problem. This hard problem is actually consuming the time. Okay, in this case, the tool would say like, all right, I will return to this later on. I'm moving to the next cluster, verifying the next cluster, moving to the cluster n plus 1, and so on. And then it returns to this hard problem and then allocates the resources necessary for this hard problem to be fixed. This is in one-spin DV inspect is done with some strategies that will help to to get better convergence when it comes to top level designs. When it comes to the DV inspect, we have a verification report that is usually reporting the necessary results. And this is a way to analyze what's being, what did converge over night or over the weekend. You come back and you see that if your sign-off criteria is being satisfied, you will get the green part, and then you can generate a more detailed report. But if you coming next morning or beginning of the week and see that, okay, I still have red parts or yellow parts that still did not converge, then it would be interesting to allocate more resources and attention to this specific part. It is important to distinguish between the type of checks that are being checked. As you've seen, we have safe RTL checks, which are the most important ones, and they need to be verified. They need to hold at block level, and then the reachability analysis needs to also is important to get all the states in the FSM, to get all the dead code being the hit. Of course, in some cases, formal work together with simulation. Therefore, the coverage is collected from both techniques in some common in a joint report, I would say, or joint database. And it is important to get the dead code analysis, the FSM analysis, and toggle aka stick checks into the and provide this information to the simulator such that the simulation does not spend time on it. And here is the one-spin coverage closure analysis accelerator app. So, and this solves the problem. So basically, excuse me, this analyzes the design and finds these unreachable coverage targets and provides this information to other tools in the flow. And the coverage viewer ignores these targets when calculating the metrics. User can also, not only for the failing targets, also for the wave targets in OneSpin can generate these hinters or waivers to provide to the simulation flow and to increase the coverage, therefore close the coverage faster. All right. Yeah, so summing up, so OneSpin DV inspect is a push button verification flow. It doesn't need to specify any input stimuli or to drive any vector, and it comes with a debugging environment where one can debug why and how actually the specific behavior is triggered. It comes also with reporting, so that can one analyze the results that are coming overnight, over 1 hour, doesn't matter. And it scales well when it comes to the top level design. In order to accelerate this, usually the complexity is hitting in, and we work on how to convert on these specific checks. I hope this was useful and informative. I would like to thank everyone who attended. And if you have any questions, feel free to ask. I think we have 10 minutes left from the allocated time, so I will answer the questions that are coming in. And of course, you can also reach me out after the conference. I will happily reply to your questions, and thank you again. So yeah, this concludes my talk for today. Thank you very much. right, so looks like in the chat we don't have any questions. So okay, so we have a question from Cedric. Can we somehow merge results from a few block level auto checks into one big report? Well, technically you can. I don't see a way not to do it. It depends, of course, what flow you're going to use to merge these results. And I believe we would need to discover more on what is the exact specifics of the integration of block level into a bigger report. So ideally, Cedric, would be that the block level are run on the top, at the top level as well, specifically if we are talking about reachability analysis, because the reachability checks, when we move the hierarchy up, they are influenced by this moving, by this increment of the hierarchy. So I hope this answers the question. All right, then we have a question from Xiu Liang. So nowadays, is this RTL code written more from scratch or generated with the help of some tools? This check may be moved forward if later way is chosen. Any support for that? Well, from one point of view, from the software point of view, there is no limitation. When I would say, like, is it written? Doesn't matter if it's written or generated. But if it is generated, I believe that this having some rules there can help. But I honestly cannot answer this question in so much detail. Okay, so again, thank you very much for joining today tutorial. If you have any question, write me a mail. I will happily answer. Okay, we have one more question from Rehab. Is that measured in reference to lines of code? When you mentioned the coverage, is it measured in reference to lines of code?
Morgen nog optioneel is, want ik weet niet hoe dat je wakker wordt morgen. Maar dat zou ik wel doen.
Dat gezegd van, we zouden nu als dat morgen erop zetten van 10 tot 8 als bijkomende gewoon extra shift.
Ja. Nee, morgen kan ik wel rijden eventueel.
Nee, maar ze zei van bel.
Kan ik niet rijden.
Ze zei gewoon van belt mij gewoon de moment dat je wakker bent en dan hoor ik het wel. En donderdag zien we wat we dan nog regelen. Ik wil gerust een nacht overpakken, maar dan moet jij vrijdag gewoon een dagshift doen.
Ja, maar dat gaan sowieso, denk ik. Hè?
Maar ik heb ook gezegd van als ik vrijdag nog echt ziek ben, dan is er wel echt iets veranderd.
All right. Yeah, so it's measured in statement coverage. It's measured in statement coverage and branch coverage. So the coverage that is being exported from reachability analysis, let's say, so for that code check is statement and branch coverage. For FSM is FSM, for toggle is toggle. Very welcome. Okay, so if there are no more questions, again, I would like to thank everyone